Okay, so here's a circle. And you can see I have my, I've described, actually I don't know how to do polar coordinates in Desmos, so I'm describing an x and y coordinate as r, which is this p over 1 plus, it's supposed to be epsilon cosine t, but I'd use q for epsilon.
Alright.
And the y coordinate was r sine theta, the x coordinate is r cosine theta. So, but I just used our program from yesterday, and you can see here, why don't you move q around a little bit? That's our epsilon, and I said as it goes between 0 and 1, you become closer and closer to, you become more and more like an ellipse. You see that?
Yeah. So maybe about 0.5.
Yeah, so there's an ellipse, and you can, I can go way big ellipse, or I can go back to a circle. And as I move this p around, it just sort of makes it grows the size of it. So I'm gonna leave p initially at 1.
All right.
But I do have some relationships between epsilon and p for orbits of particular planets.
Yep.
So the first thing I want to do is what I have going on here, and this is to show why the planet's orbits or satellite orbits are a little bit more complicated. I have the velocity being displayed right now. I'm going to display a vector that goes right back to the origin.
Okay.
And separately from that, I'm going to display the acceleration vector.
Okay.
Okay. Here we go. Okay, so for a circle, the acceleration is right back to the origin, just like we saw before. But I want you to change the ellipse just a little bit, or wherever you want, actually. Just make it.
Yeah, sure.
Okay. So the black is the acceleration, and the blue is just a line that goes right back to the origin.
All right.
So it looks like the black endpoint is actually tracing its own ellipse
Around that origin point.
Yeah, I don't know if it's an ellipse or not, but it's certainly not sticking to the origin.
It's not.
So our acceleration is diverging from the origin. And can you make this path even more of an ellipse? But hold on, let me zoom in a little bit since I ended up making it a little smaller than I intended to. Can you change that Q and make it a little bit more elliptical even?
So it's hugely varying.
Okay, so we know, or scientists know, you guys will be learning, that like for a satellite orbiting the Earth is always pulling the satellite back to it.
Yeah.
And so the acceleration should always be right back to the Earth. And we can see the black line is the acceleration here, and that's not being pulled right back to the Earth.
Yeah.
But nonetheless, we know from Katherine Johnson's paper that this path is the orbit of a satellite. So it tells you that there's a little bit more going on than just knowing the orbit. And so I want to ask you, I'm going to get rid of the acceleration vectors and ask you if you think this path being traced out here looks weird. So I'll get rid of the acceleration, and I guess I don't. No, I'll keep the path, and I'll keep the velocity vector in red. Okay. So let's go. Actually, let's go to let me just turn the camera on and off. We'll go to the next movie.